So we will talk about how to determine the B1, B2, B3. It's the same scheme. So we again do a Taylor expansion, but it's a bit different because we are dealing with a time problem where the things are different. So I'll just write our scheme again. So un plus 1 is equal to un plus delta t summation k is equal to b0 to 3 bk del u del t at n minus k. So you start by, you want to expand all these terms around the current time instant, okay, in Taylor series. So you will write un plus 1 is equal to un plus delta t times del u del t at n plus delta t square by 2 factorial del u del t at n plus 1, sorry, del 2u del t2 at n plus del 2 cube 3 factorial del u del 3u del t3 n plus order delta t to the power 4. So this is taking care of the un plus 1. You would also want to expand the del u del t around the del u del t at earlier times in terms of the del u del t at the current time. So you will write del u del t at n minus 1 is del u del t at n minus delta t del u del 2u del t2 at n plus delta t square by 2 factorial del 3u del t3 n plus order del t cube. And similarly for your later times, earlier times, sorry, n minus 2 is del u del t at n. Now there are two time steps, is 2 delta t del 2u del t2 n plus 4 delta t square by 2 factorial del 3u del t3 n plus order delta t, and so on for the n minus 2, n minus 3 also. So then you again you will bring everything together. You will write this expansion of un plus 1 in term instead of this one. Un is as it is, and then delta t summation this time. So b0 into del u del t will not change because that's at the current instant, but then b1 times this quantity. So you will have b1 times this, b2 times this, and similarly these are all pluses, plus b3 times the del u del t at n minus 3. We just got the 3 delta t here and the 9 delta t square by 2 factorial here, and similar things. So when you now look at all these things together, there is a un is equal to un trivially, and b0 del u del t at n is equal to b0 del u del t at n. You don't do anything with, you don't mess with them. So then you evaluate this stencil by just adding all these things on the right hand side and compare them with the left hand side, and you have to find out the b's from them. So if you were to aim for the maximum Taylor accuracy, then you will have 4 equations and 4 unknowns, but we don't want that. You will have 3 equations in the 4 unknowns. So by restricting the number of derivatives which we zero, the number of higher order derivatives that we want to zero, you will end up with a relation. You'll have then 3 equations and 4 unknowns. So you'll have 3 equations in the 4 unknowns. So I invite you to find those things, and what you will end up with is a relation between them. So you'll have B1 is equal to minus 3B0 plus 53 by 12. B2 is equal to 3B0 minus 16 by 3, and B3 is equal to minus B0 plus 23 by 12. So this will give you one less order of accuracy than is possible with the three level scheme, but you live with that reduction in order to be able to optimize your cost function in terms of B0, and you will get the values of B0, and from this relation you will get the values of the other three coefficients that will optimize your stencil behavior. Now we would also want to plot and see how is our scheme doing, because that plotting gives us a feel for it. Now there is a problem. Okay, so I'll write out the equation again that we found. The one that we want to plot is this omega tilde. So omega tilde delta t we found to be I e to the power minus I omega delta t minus 1 by summation k is equal to 0 to 3 bk e to the power I k omega delta t. So the natural thing to do following especially on our spatial discretization is to think of this as omega tilde delta t being the dependent variable and omega delta t being our choice. That's the natural thing to do. So Tam does the flipping. So he is suggesting, and you have to argue for me, that he is thinking of this as omega delta t as a function of omega tilde delta t. So we'll want to plot omega delta t versus omega tilde delta t, and then look at its real part and imaginary part. Okay. So there are several open questions here, but can you think of why this might be the way to look at it, rather than in the spatial scheme we had a similar looking result that alpha tilde delta t was some function of alpha delta t times delta x there, delta x, and we were making plots of alpha tilde delta x versus alpha delta x to get a visual feel of our stencil. So why might this be the better, or this be the appropriate way, not the better, the appropriate way of looking at our stencil? That is to start off with. Then we'll look at, or you can look at complex omega tilde delta t also. If you have in your problem, if you have got time decaying or time growing sources. In many cases, you know the analytical solution. In fact, for the problem that you're going to address for your homework, you will know because it's a nice problem. So you'll know the analytical solution. And so in those cases, you know the future, and even if you don't know the future, this is just for analysis purpose. So from that perspective, so I would debate you that this is equivalent, these two are equivalent, and you should be looking at the time scheme also in the same perspective. So similarly, say you don't know the derivative in many cases, or you can argue that, so then here also we should have looked at it in the opposite way. That's not really the case, right? So weightage you have to choose. As a designer of the scheme, you still have to choose, and there are good and bad choices to be made. But this is a flipping of our perspective itself. We have to flip our perspective when we are in time. So instead of me giving you the answer, I'll let you think about it. Okay. So if you go with this indeed as the way to look at it, then it turns out that so omega delta t is the output of your analysis. And so what we will be looking at is, we can then think of e to the power I omega delta t can be a variable. Okay, that is the output variable. So let us choose, so let z tilde is equal to omega tilde delta t, and or no, don't. So let z be e to the power I omega delta t, and this is the output variable. There is a dependent variable. So if you plug that in, then what we get is omega tilde delta t is equal to I z minus 1, 1 by z minus 1 by summation k is equal to 0 to 3 bk. So this is z to the power k, sorry, z to the power k. So this is z to the power k. So if you now bring this to this one side, because remember now omega delta t is the independent variable. So you can do the manipulation and you will find out that you can come up with a polynomial equation which will be a fourth order polynomial. So there will be z4 plus say some gamma 1 z cube plus gamma 2 z square plus gamma 3 z cube z plus gamma 4 equal to 0. So you'll come up with a polynomial. You can see that directly because there is z cube here. There is another 1 by z here. So you will multiply, get a z to the power 4 term. Okay, and of course these gammas are dependent on the omega tilde delta t that you have. So this is a polynomial equation for your z, and it's a fourth order polynomial. Then what do you do with this? Where all the gammas are functions of my omega tilde delta t. For a single omega tilde delta t choice, there are 4 solutions because it's a fourth order polynomial. So those are the 4 roots of this polynomial, and those are all complex in general. This gammas are also complex. So what you will find is that z1, z2, z3, z4 are separate functions of omega tilde delta t, and these are all complex. So this is a plot of the real part of omega delta t, which is the real part of z, versus the omega tilde delta t on the x-axis. So this is that plot, and there are 4 solutions. These are the 4 roots, how they vary with various choices of omega tilde delta t. Here omega bar here. So what we would want is that as omega delta t, omega bar delta t increases, the real part of omega delta t should also go the same. We want the 45-degree line. So that solid line is a 45-degree line, and we see only one of these roots is hugging that for some distance, small here. So there is stopping around 0.5, if you may. All the others are doing nothing close by. Yeah, they are all over the place. Then you look at the, so this is the imaginary part. Again the 4 solutions. So I'll zoom out and you can see all of them together. But again now the 4 solutions, and now you would want your, so right now we are looking at omega bar as real. So you'd want your output omega to have 0 imaginary part. So nothing should be here. So you'd want that solid line again, and only that dotted line is somewhere close to 0 in the initial stages, and again it is departing. It is going negative. Negative means negative is increasing. So we had, remember, e to the power I omega delta t, so which is e to the power I omega r plus I omega I delta t, e to the power, there was a minus, is it? Oh, minus. So remember our the inverse Fourier transform was Laplace transform was this thing. So there was a minus there. So that becomes minus omega r delta t times e to the power minus minus plus omega I delta t minus into minus 1, so plus 1. So you're right. So omega I negative is decaying. So it's a decaying solution, but you don't even want that. And there are some solution which is growing, which is even worse, because you would want a stable solution, and if it's decaying, okay, but that one is going to blow up and it's going to kill you over some very short time horizon. If that root is allowed to, so if you choose your omega bar delta t to be too large, that is, you choose your delta t to be too large for the frequencies that are there in your solution, which you don't know beforehand, but you should have a sense of that. Then you will end up with those high frequency problems to now make your solution become diverging. Otherwise, your optimization will be very bad. So that's the optimal solution, and the others are what are called marked the spurious roots. So there are these spurious roots. Okay. So stable range is marked out as wherever this crossing is, wherever this one root becomes positive, so that this becomes unstable, this becomes a growing solution, and so that you definitely need your omega delta or omega bar delta t to be less than that. Now there are other considerations that within that less than that, are you satisfied with the amount of deviation that will be there here if you zoom in between your dotted root, which is following the real part properly. If you would want that to be, how far deviation should be there, how much of decay you can allow in the true solution. So again, these are designer choices, and TAM with his experience came up with some choices and some recommendations. We'll talk about that. The other thing to look at, of course, is also you should be zooming into this and trying to see how far the deviation is. It's almost looks to be very good till 0.5, but if you zoom in, you will have other answers, okay, about how much of the deviation is there. So this is the optimal stencil with the B zeros which are obtained for, okay, I should say some choice of sigma and xi. So the choices of sigma and xi. So sigma is 0.36. So we are giving more weightage to the imaginary part being close to the desired one, and xi is 0.5. So you wanted your, or you chose, or he chose to look at 0.5 the range, so that is right here, and so the scheme seems to be doing well here also. So in that sense, he's doing a good job. So over that 0.5 range, his imaginary part is also close to 0, and the real part is also close to the truth. But this other guy has shot off, so crossed into the danger territory beforehand also. So you have to curtail your ambitions. So this turns out to be some 0.41 instead of 0.5. So you cannot get to 0.5. So you have to choose your delta t so that the omega bar delta t should be less than 0.41 for stability. So this is an absolute must. But then if you also are more finicky, which you should be, about the damping of your solution because of how much it will diverge, it looks to be very small, but you might be more finicky. And so TAM in the final recommendation is suggesting 0.19 for accuracy, so more conservative. So with this, the imaginary part of omega delta t on the root that you care about, that will come out to be minus 0.12 into 10 to the power minus 4, and that satisfied him. So very small deviation. You will have some decay. Okay, that is, so if you were to run it for 10 to the power 4 times the maximum period in your solution, you will see full decay of 0.12. Okay. So that one will be there, but that will be there in any scheme. You cannot get any much better with that. So again, the the period of your largest period of your solution, that is the longest period phenomenon that is there in your source, that one will determine your smallest value of omega bar. And so that one, if you bring it down here, you will get the possible largest value of delta t that you can choose. You have to be restrictive, more restrictive, you have to take small steps, which is the essence of most numericals. Yes.
Want to ask about earlier analysis, we are assuming that we had in the spatial sense, we had a wave solution, and how much is our discretization to preserving that wave?
Wave length or wave number, yes. So again, you please think about this. So it will become obvious why he has flipped the perspective, but this perspective is the right one to take. So, I invite you to please think about it for 3 days, and then we'll come back and discuss it. Definitely, I promise you that. So this is all analysis based on if you have got real frequencies only, if there is no decay or growth in your source that you have in your domain. If that is there, then you have to enlarge your, so you cannot just live with real omega bar delta t, and you will end up with plots like this, where you will now plot a region of stability in the complex omega bar delta t plane, where this is now the complex, this is the input still, this is just the input, real part and imaginary part. If you have, then you can now, or the recommendation is that your choice of delta t should be such that your omega bar delta t lives within this arc. Okay, so it's somewhere here. So that is a choice, that is the recommended way of choosing the delta t if you want to ensure good accuracy and stability. This is just for stability, by the way, in case of imaginary part being also there in your input, that is there are decaying or growing parts of your solution. Region is, that's the boundary. So yeah, so typically smaller delta t's will be no problem, but you would want to take the largest step size so that you can reach your final prediction horizon as fast as possible with fewer steps. And so this is the outer limit of that. Just like that 0.19 here was the outer limit. So anything less than that will be fine.